and final objective to understand regulation and control of the cardiac output. So we've spoken a lot about the structure of the heart, the electrical activity of the heart, the phases of the cardiac cycle. What we're going to do is put all of that together and speak about how is the heart function regulated. We refer to the total volume of blood that is moved through the ventricle as the cardiac output. But what are the factors that can regulate that? What are the hormones, the neurons, the various other systems that play a part in regulating cardiac function? So we can think about the formula for cardiac output as the stroke volume times the heart rate. So this is a product, and this is also a rate times a volume. So that's going to tell us what is the total amount of blood ejected from the heart per minute, right? Per unit time. Now, the volume measurement for that is about 5 liters per minute at rest. And then this can go much higher during states of exertion, exercise, even fatigue, etc. And then the average blood volume, so how much blood is actually circulating in your vasculature is about 5.5 liters. So looking at these two volumes is pretty fascinating because it means that your heart can turn over or circulate its entire average blood volume in a single minute at rest. Okay, very, very fascinating. All the blood in your body can pass through your cardiac chambers in a single minute at rest. So that tells us a lot about the work that the heart does and the constant supply to perfuse all of our vasculature, all of our organs. Now, when we look at that formula, we can think about factors that are affecting each part of the formula separately, which are going to overall affect cardiac output. So what are factors that affect heart rate separately, and what are factors that affect stroke volume separately? And then those two things, when combined, are obviously going to have some impact on your overall cardiac output. So the heart rate and stroke volume are both regulated by extrinsic and intrinsic factors. Extrinsic being things outside of the heart. So neuronal input or neurons, this is the sympathetic system, the parasympathetic system, and then hormones. So hormones like acetylcholine, not acetylcholine, excuse me, norepinephrine or epinephrine, which are released into the blood as hormones. Those can act on regulating cardiac function as well. So there's two types of input that are coming extrinsically or externally to help regulate the cardiac output. Intrinsic will be factors like autoregulation, which are things that are within the heart. So an example of autoregulation is the response to the heart in relation to stretch of the ventricular and atrial walls. So as the heart muscle expands to stretch more, it increases its contractility. So that is an example of autoregulation. So this is an intrinsic factor or mechanism that can control the heart rate from within itself. Okay, now let's remind ourselves of the autonomic nervous system and how it involves various divisions, the parasympathetic by way of cranial nerves. This example is going to be the vagus nerve, which supplies the contractile, the pacemaker cells, excuse me, which are the SA node and AV nodal cells. So this is something we want to really make a point of early. The parasympathetic system has an influence more on the heart rate. It doesn't really affect the contractile cells, which are the myocardial cells, the way the sympathetic system does. So we'll look at this again later on, but when we think about the parasympathetic influence in the heart, it's mainly going to be on the influence to the pacemaker cells, the SA node and AV node, and not so much to the ventricular cells. The sympathetic influence, however, which is by way of the thoracolumbar segments of the spinal cord, preganglionic neurons synapsing onto the sympathetic chain, and then postganglionic neurons, much longer in length, synapsing onto these various cardiac cells. Notice here it's going to be both the pacemaker cells and the contractile cells of ventricular myocardium. So the sympathetic system has influence on both types of cells, whereas parasympathetic is mainly influencing the pacemaker cells or the SA and AV nodal cells. Now, the heart rate will be determined by the firing frequency of the SA nodal cells. And if you look at their intrinsic firing rate, it's about 100 beats per minute. However, that is in the absence of any neuronal input, any hormonal input. And so if you were to take an SA nodal pacemaker cell and put it outside of the body into a petri dish, for example, it would generate 100 action potentials per minute. But because it is under the influence of our neurons, of the parasympathetic system, which is slightly more predominant than the sympathetic system, it's going to slow that firing rate to about 70, 75 beats per minute, which is where we get our resting heart rate from. So we want to think about the intrinsic firing rate of these pacemaker cells, but also how our nervous system and our hormones actually regulate that to be about 75 beats per minute. All right. So whenever we're in states of rest, the heart rate is lower, but when we have states of exertion or excitement, it can go all the way up to 100, which is its intrinsic firing rate. Now, the way that happens is a series of events, starting with the nervous system, starting with the sympathetic activity by way of neurotransmitter or hormone, right? Remember, this can be both with a sympathetic system. It's going to bind to beta-1 receptors, which are the specific type of adrenergic receptors found on the heart. And that is going to result in events which are usually opening sodium or calcium channels, which are going to result in depolarization, and that is going to increase the heart rate. Now, the way that this happens is because opening up of these channels just make it easier, make it more favorable, make it more likely for the depolarization, the spontaneous depolarization of these already depolarizing pacemaker cells. So that in and of itself is what speeds up the heart rate. Okay, it's just easier to depolarize these cells. So let's look at some of the mechanisms for this event. So we have the hormone or neurotransmitter binding to beta-1 receptors. These are coupled to G-stimulatory proteins. Alpha subunit activates this amplifier enzyme, adenylate cyclase, which in turn turns on the second messenger, cyclic AMP. And what that ultimately results in by way of protein kinase is opening up of funny channels, which we know are crucial to the ionic movement of the pacemaker cell, as well as opening up of T-type calcium channels, which are also crucial in getting us to the depolarization, right? So the events that are triggered from the neuronal input and the hormonal input result in opening up of the channels that make it favorable to depolarize these pacemaker cells. So in doing so, we're going to increase the likelihood of firing action potentials, which is going to increase the heart rate. Okay. Let's look at the opposite turn of events. Let's look at the parasympathetic influence. And this is by way of the vagus nerve, which is our 10th cranial nerve. So that is going to result in muscarinic cholinergic receptors. Remember, the parasympathetic system has different receptors altogether, different neurotransmitter altogether. So this will be acetylcholine binding to a muscarinic type of cholinergic receptor, and then that resulting in the opening of potassium channels or the closing of calcium channels. So you can either close calcium channels, which make it harder to depolarize, or open potassium channels, which also would make it harder to depolarize as they put the cell more in a hyperpolarized or repolarization state. So both of those events make it more difficult, make it harder, make it less favorable for the pacemaker cell to fire an action potential, which is ultimately going to decrease the heart rate. Okay. And the events for that, so decreasing the heart rate would be closing calcium channels, right? So first here's our muscarinic cholinergic receptor. Acetylcholine leaves that postganglionic neuron, binds to this receptor, and that triggers two options or two types of events. One is closing calcium channels, again, resulting in hyperpolarization because you make it harder to depolarize. Two is opening up potassium channels, and because of the ECDF of potassium, which is leaving the cell, we're also going to make it hard to depolarize slash hyperpolarize. So both of these result in um, a slowed threshold to get to fire and action potential, and so that will decrease the heart rate. So here's a graph just comparing those two events. Here's our membrane potential. Here's rest -70, -50 our threshold, and then up to more positive membrane potential. Here's our time. Now notice that the gray curve is sort of the resting curve. We're going to fire two action potentials within this 0.8 second span. Now, if we were to engage the sympathetic system, notice we're going to make it easier to depolarize. So we're going to fire three action potentials in that same time frame. Alternatively, if we had the parasympathetic system more engaged, it would become more harder, it would become more difficult, less favorable to fire an action potential. And so we would only fire one action potential, which is the purple curve, in that same time span. Yes, exactly. So thank you for clarifying that. So I'm going to go back to the previous image. These are not on the same cell surface. So these are just two options that could happen still on pacemaker cells, but on different types of pacemaker cells for different reasons. We can have either of these events take place that would both result in hyperpolarization or decreasing the heart rate. Okay. Now let's think about the hormonal control. The hormonal control is going to be the same as the sympathetic system. We know that the norepinephrine slash epinephrine can act the very same way, either as a neurotransmitter or as a hormone. So the effect is going to be the exact same based upon epinephrine as a hormone. We're also going to see increase in the action potential frequency because of that same sympathetic effect. And then we're going to see an increase in the velocity of action potential conduction in the muscle fibers, which is we're also going to see an increase in the contractility. Remember, the sympathetic system affects the SA node and AV node, as well as the contractile cells of the actual ventricular myocardium, ventricular myocardium. Okay. And then glucagon, which is another hormone, can also play a role to increase the heart rate. We sort of looked at this when we talked about the fed and fasted state in the endocrine system. So glucagon can also put the body in this fight or flight state and increase the heart rate as well, right? The hormone of the fasted state. And then integrating the heart rate control, we can think about how the sympathetic neurons affect the heart rate. Parasympathetic neurons can lower the heart rate, and then the circulating levels of epinephrine as a hormone can also increase the heart rate. So just kind of putting it all together here, the sympathetic system, either as a neuron or as epinephrine, can both increase the heart rate, and then parasympathetic system as a neuron only can lower or decrease the heart rate.